We are still in our operations research course. Today, we will take our first example on linear programming problem. As we can see in front of us, we have an example that's coming from a real life situation. So we have a wood carving company that produces two types of wooden toys. They produce soldiers and trains. The soldier sells for $27 and uses $10 worth of raw material. Each soldier is manufactured each soldier that is manufactured increases the company variable labor and overhead cost by $14. A train, on the other hand, sells for $21 and uses $9 worth of raw material. That's the material cost on the company. So each train built increases the company variable labor and overhead cost by $10. So the manufacturer of wooden soldiers and trains needs two types of skilled laborers in order to produce those kind of toys. The company needs carpentry and finishing. So the soldier requires 2 hours of finishing labor and 1 hour of carpentry labor to do that. The train requires 1 hour of finishing and 1 hour of carpentry labor. So each week, this company can obtain all the needed raw material, but only 100 finishing hours and 80 carpenting hours needed. So the demand for trains is unlimited, and the demand for soldiers is only 40 soldiers a week, as we can see in here. The company needs to maximize the weekly profit, which is the revenue minus the cost. What we are asked to do is to formulate a mathematical model for this company situation so that it can be used to maximize the company's weekly profit. So we focus on this. The company needs to maximize the weekly profit. As we can see, it's a medium to a hard real life situation. Like there's a lot of variables playing inside the equation. That's why we keep emphasizing that linear programming is a very nice tool in order to solve medium to high complexity situations in companies. Even those situations could be way more complicated than this, but linear programming will make it linear and easy to see the big picture and solve it, and eventually optimizing the problem by maximizing or minimizing the variables needed. So, in order to develop the company's satisfying model, we will explore the characteristics shared by all the linear programming problems. So what you will see here is almost similar to any linear programming problem that you may face in your real life. So, starting with the decision variables. So first, we defined the relevant decision variables. So any linear programming model, decision variables need to be completely describing the decision to be made. In this case, the wood creating company or the wooden toys company. So the company needs to decide how many soldiers and trains need to be manufactured each week so that it can get the best optimized result. So first, we assume x1 to be the number of soldiers produced each week and x2 number of trains produced each week. So those are decision variables helping us to construct our model and reach our final solution. Objective function, for any linear programming problem, decision maker need to maximize or minimize some functions of decision variables. Maximizing could be revenue or profit. Minimize usually is the cost, if the cost is involved in your problem. So as we mentioned previously, the function to be maximized or minimized called an objective function. That's your objective. That's your goal from solving this problem. You need to maximize or minimize certain variables. So for our current problem, we can realize that there is fixed costs like rent and insurance, etc. They don't depend on the value of x1 and x2. So the company can concentrate on maximizing the weekly revenue minus the raw material that they purchase and minus the other variable costs, as we will see. So taking the weekly revenue separately, we can say the weekly revenues equals the weekly revenues from soldiers plus the weekly revenues from trains. This can be translated as dollars over soldiers multiplied by dollars by soldiers produced by week, plus dollars per train multiplied by trains produced by week. Having the assumption that x1 is related to soldiers produced each week, x2 trains produced each week, and back to the fixed costs and variables, fixed costs and constants mentioned earlier in the problem, we can say that 27, that's the cost of the soldier, multiplied by x1, number of soldiers being sold by week, plus 21, that's the price of a train, multiplied by x2, which is the number of trains sold per week. So here we can translate this this kind of writing can be represented in numbers. So we have 27 multiplied by x1 plus 21 multiplied by x2. Also, we can say the weekly raw material cost to be equal to, we said its overhead cost increased by the soldiers is 10 multiplied by x1, because depending on number of soldiers we produce per week, plus 9 for the trains multiplied by x2. For the other weekly costs, we can say 14 multiplied by x1 plus 10 multiplied by x2. Let's go back to the problem. So we can see here the overhead costs related to this soldier, $14, and the overhead cost that's considered others generated related to the train is $10. So multiplied 14x1 plus 10x2. Those are steps toward generating our final model representation for the problem. So the company needs to maximize the summation of all summation of cost the summation of the revenue, which is the cost of each product sold, minus the other costs and the raw material that the factory pays out of pocket. So we can say here, need to maximize the 27x1 plus 21x2 minus 10x1 plus 9x2 minus 14x1 plus 10x2, and this will give you, if you do the summation and subtraction, you can get 3x1 plus 2x2. So your ultimate goal in this problem is to maximize 3x1 plus 2x2. Usually we represent that as max the variable z, which is equals 3x1 plus 2x2. So in this case, you generated a model that represent what this problem need to achieve. That's the golden rule, or the golden equation that all the problem that we read earlier is related to. That's what they are trying to say in terms of numbers. Since we are using a linear programming problem to optimize this kind of model, then as we mentioned earlier, we need to look into constraints. In terms of constraints, we can say as x1 and x2 increase, the company objective function will be larger. That means the company is free to choose any value of x1 and x2, and the company can make a random large profit by choosing x1 and x2 to be very large. But the bad thing is the values of x1 and x2 are limited by restrictions and constraints that are written in the problem. So the constraint number 1, as we can see here, each week the maximum number of hours of finishing available are 100 hours. For a lack of operators or for certain constraints about the real life situation of the factory, there's only 100 hours can be spent by week for finishing. And the constraint number 2, there's only 80 hours maximum of carpentry that can be used. That's another constraint. Constraint number 3, there is a limited demand on soldiers to be 40 each week. So you can't produce 80 because you will be losing. You will have 40 soldiers being on the shelf. You need to produce as much, or in real life a little bit more than what the demand is, but you can't produce double what the demand is, then you will be losing money. With that being said, then you can say the constraints expressed earlier can be represented in the following equation. So you have total finishing hours equals finishing hours per soldier multiplied by soldiers made per week, plus the finishing hours per train multiplied by trains made per week. And that can be represented in variables form, or can be represented in numbers and letters. So that can be 2 multiplied by x1 plus 1 multiplied by x2, and this can be said to be 2x1 plus x2. That's the finishing constraint. From that we can say 2x1 plus x2, as we mentioned in constraint 1, cannot exceed 100 hours per week, so it will be less or equal to 100. So that's the first constraint equation. For the second constraint, carpentry is less or equal to 80 hours a week, so we can say total carpentry hours equal carpentry hours over soldiers multiplied by soldiers delivered per week plus carpentry hours over train multiplied by train per week. And this need to be represented in an equation form as well. So we can say 1 multiplied by x1 plus 1 multiplied by x2. From that can be simplified as x1 plus x2, and we said x1 plus x2 for carpentry cannot exceed, so it will be less or equal to 80. So this is constraint, so this is constraint number 1, and this is constraint number 2. So we had our golden equation, we had our main equation. Now we are building our constraints. For constraint number 3, so there should be only 40 soldiers to be produced. We represented earlier soldiers as x1, so we can say simply x1 less or equal to 40 per week. So that's constraint number 3. Now another constraint that always show up, need to keep in mind, there is no single line in the problem, not necessarily there's a line telling you about it, but it's a common sense, because you are dealing with real life problems, then you should use your best practice of judgment to tell if that constraint need to be included or not. That constraint is the signs restriction. Do we have a restriction of signs for our values or no? So to complete the formulation of linear programming problem, then the question that should be answered, can the decision variable only assume non-negative values, or the decision variables allowed to assume both positive and negative values? So you can't say if you have a real life physical problem that it involves pressure, then you can if you can't tell some physical values to be in minus. Let's say if the pressure is non-directional, then you want to tell in minus. If there is a rules that prevent you from doing that, then you can't do it. So in our case, for that specific restriction, if the decision variables xi can only assume non-negative values, then we add the sign restriction to have xi plus xi larger or equal to 0, which is x1 larger or equal to 0, x2 larger or equal to 0. If not, then no need to put that restriction. So in our case there is a sign restriction, and that's because we are trying to maximize. We don't want our cost, or it's not applicable for this exact problem, to have the cost in minus. So you are having a physical values of costs for the soldier and the train. We're not saying the train cost minus $2, like I'll give you $2 to take the train. Doesn't make sense. So we can say either xi larger or equal to 0, or so we can say here either xi larger or equal to 0, or we can say separately x1 larger or equal to 0 and x2 larger or equal to 0 so can't be in minus. So that's constraint number 4 and constraint number 5. So having all those constraints with the golden main equation of optimization for this specific problem, then we can say that we are ready to solve this problem. And that's what we will learn in the future, how to solve an optimization problem using various methods of optimization.